So continuing on our definite integrals and applying the fundamental theorem of calculus, which is basically the first fundamental theorem of calculus. So last time we looked at simple examples, practiced a lot of them, and I hope you have practiced the problems which I had asked you earlier to do. So let me just once again show you the problems I was talking about. These are the practice problems, guys. I hope you have done them. And now what we're going to do is we are going to look at a little bit more difficult examples. So let's look at the first example here. We have an absolute value function. Now before we can apply the fundamental theorem of calculus, we have to first work with the absolute value. Now if you guys remember that, I'm going to start with a very simple thing, that absolute value of x is defined to be x when x is greater than or equal to 0, or minus x when x is strictly less than 0. So on this basis, first of all, we are going to work with this one. So let's apply it on the absolute value of 2x minus 5. So using the same scenario as earlier, we're going to say this is 2x minus 5 when 2x minus 5 is greater than or equal to 0, or 2x is greater than or equal to 5, or x is greater than or equal to 5 halves. Okay? And it will be the same thing, will be negative of 2x minus 5 when x is strictly less than 5 halves. To see a cleaner version of it, we can write this as 2x minus 5 when x is greater than or equal to not 5, just make it life simple, 2.5, and minus of 2x plus 5 when x is strictly less than 2.5. Okay, so in other words, when your x is greater than 2.5, you have a different function, and when x is strictly less than 2.5, you have a different kind of function. Now, if you remember from your integral rules, that if you have a midway, like I'm just going to write that down as a remembrance, that if you had a to b fx dx, you could write this as a to c f dx plus c to b f dx, where c is a value in between. So notice 2.5, keeping that in mind, 2.5 is a value between 0 and 5. So we're going to apply that here, this idea. So now our original function is now going to be written as 0 to 2.5. Okay, now when you do the math, guys, keep in mind from 0 to 2.5, that is x is less than, this is the expression we have to write. So this is negative 2x plus 5 dx. Okay, plus. Now you go from 2.5 to 5 because that's where it is ending. The upper level of the limit of the integral is 5. So we go from 2.5 to 5. Now this is the expression we will be writing because this is x greater than or equal to 2.5. 2x minus 5 dx. And after that you are just simply going to solve it. So first thing, we look at the first one. So this one is minus 2x squared over 2. I'm simply going to write this one as minus x squared plus 5x. And we are going to go from 0 to 2.5. Now this one is going to be plus expression inside, that is the entire derivative, is x squared minus 5x 2.5 to 5. Now remember, guys, this is the entire derivative. It is fx, and this one is fx here. So when we apply the first fundamental theorem of calculus, or the fundamental theorem of calculus here, it's going to be f of 2.5 minus f of 0 for the first expression plus f of 5 minus f of 2.5. Now when you plug in 0, notice all the terms are having x's, that will be a 0. So what is f of 2.5? So it's going to be negative 2.5 square plus 5 times 2.5. Okay. And the next term is already 0, minus 0. Okay. And then f of 5. So this f of 5 is what? 5 square minus 5 times 5. So basically this also becomes 0. Minus f of 2.5 would be, remember, keep your brackets handy. It's 2.5 the square minus 5 times 2.5. Okay, so this one is also 0. So what do you get here? You are going to get is minus 6.25 plus 12.5, and you're opening this up, it's going to be minus, or take the brackets inside, 6.25 minus 12.5. When you do the whole math of this one, open this up, the final answer is 12.5. Okay, you can do this calculation. The main important part, guys, is when you're looking at an absolute value function, you have to remember the definition of the absolute value. Okay, now let's look at some integrals involving trigonometric functions. Okay, so the first one, guys. Now, if you remember the Pythagorean theorem, we all know that 1 plus tan square x is secant square x. So then this part is simple, easy, because the top and the bottom, it cancel out. Okay, so this one cancels out. What are we left with? 0 to pi fourths 1 dx. So which is the entire derivative of an integral of 1 dx is x, and 0 to pi fourths. Now remember, inside the square brackets, this is your f of x. This is the entire derivative. So it is f of pi fourths minus f of 0. Basically, it's pi fourths minus 0. Final answer, pi fourths. Okay. Now, we are going to look at the next problem. So here we have 2 plus cosine x. What are we going to do? You're going to write this as, first take the integral of the function inside, and what you get is 2x. Integral of cosine x, guys, remember, is sine x, and 0 to pi. Okay, now remember, this is your f of x. The capital F of x, sorry. So what is this? This is f of pi minus f of 0. That's when you apply the first fundamental theorem of calculus. What do we get here? So it's going to be 2 pi plus sine pi from f of pi minus, it's a 0, and plus sine of 0. So this whole part is 0. The last part is totally 0. So what do you get here? 2 pi plus sine pi. If you remember, sine pi is also 0. So final answer, 2 pi. Okay, now let's look at a problem from a different perspective. Instead of being given an integral with a function inside, you are asked the same problem but in a different way. So let's look at that problem now. It says find the area of the given region. Notice you have to learn how to write down the definite integral, and then you will apply the fundamental theorem of calculus to solve it. So the first thing is we write down the definite integral. So the definite integral here is, these are my limits, x equal to 0, x equals 3. So it goes from 0 to 3. What's the function? X plus 2 dx. And if you remember from your earlier section, when we started with integrals, the Riemann sums and definite integrals, we actually did this problem using geometric formula. And if you recollect, the geometric formula gave us the answer. So I'm talking from section 4.3. We had the same problem and we used geometric formula. And when we applied the geometric formula, the answer we got here was 10.5 square units. Now we're going to here, in this, you're going to apply the theory we have learned, that is, we're going to apply the first fundamental theorem of calculus. For that, guys, we will just simply do, now we're going to apply theory here on this left-hand side of this equation to see if it exactly comes according to what we got from the geometric formula. Okay, let's go ahead and apply it. So first we do the indefinite integral. So we're going to go from here. And we're going to have this as x squared over 2 plus 2x going from 0 to 3. Remember, this is your entire derivative. So you have to find f of 3 minus f of 0. Now f of 3 is what? 3 squared over 2 plus 2 times 3. That's f of 3 minus f of 0 is 0 over 2 plus 0. So basically this is 0. What's this? It's 9/2. So now looking at f of 3, 9/2 plus 6. Now what's 9/2 plus 6? That's basically 21 over 2 or 10.5. Now remember, it's saying find the area. So area, because they're saying the way the words are, so it's going to be 10.5 square units. Okay. So we have done problems related to absolute value functions, and also looked at some trigonometric functions, and also we're looking at from the area of a given region. So in these problems, when you talk about area of a given region, it is you have to set up the definite integral first. Once you set up the definite integral, then you apply the first fundamental theorem of calculus and you just go ahead and do the math. Okay. Now I have written down some practice problems for you guys, and I want you to practice these problems. They're similar to the problems I have done. And also, there's another slide which has find the area of the region. This one again, if you would go back to your section 4.3, it's a problem we did using geometric formula. So when you apply the first fundamental theorem of calculus here, you should be able to get the same answer as you had in the section 4.3. Okay, so guys, please go ahead and practice these problems. And next time we're going to look at a mean value theorem, average value of a function, and second fundamental theorem of calculus. Bye-bye. Thank you.